We're going to continue with this presentation, this lecture about or talk about processing using memory in DRAM. Remember that right before the break for lunch, I was talking, or I was refreshing on two proposals. One of them is row clone that can be used to perform row copy, the bulk row copy inside a DRAM subarray. The row clone paper also proposes ways of copying data between banks and also between subarrays inside the same bank. And after that, we went quickly over the AMBIT proposal that whose the basic idea of which is to activate 3 rows at the same time, and this way performing a majority operation. And with this majority operation, you can have and or depend if you fix one of the input bits to 0 or 1, and this and or can be used potentially to implement more complex operations together with the solution that the AMBIT paper proposes for NOT operation. So now, by using or by making use of these ideas, we wanted to go further and be able to implement more complex operations inside DRAM. But that wasn't a trivial thing. Why is that? Because you really need to come up with an optimized way or an optimal way of mapping the data inside the DRAM, and also design the algorithm itself or the microprogram that is going to run in the memory controller, and in order to control how different rows are activated inside the DRAM subarray. And that's what we propose in the next work that is called SIMDRAM, a framework for processing using memory in DRAM. So prior works in processing using DRAM, they have proposed processing using DRAM for sure, but they have some shortcomings, right? They don't support, or they only support basic operations such as Boolean operations and addition in the best case from some prior proposals, recent but also prior proposals, and these are not widely applicable. So they support only a limited set of operations. They lack flexibility to support new operations, and those cases or those approaches that support more complex operations such as multiplication or addition might require significant changes to the DRAM. For example, if you want to implement addition, you need to have a way of shifting bits from one bit line to another bit line if you are using a horizontal, the conventional horizontal layout, right? Because when you are adding bits, you get a carry out bit, and this carry out bit needs to go to the next bit in order to perform the addition operation correctly. So we wanted to deal with all these shortcomings. So we realized that we needed a framework that aids general adoption of processing using memory by efficiently implementing complex operations and providing flexibility to support new operations. That's the goal, designing a PUM framework that efficiently implements complex operations and provides the flexibility and everything with minimal changes to the DRAM architecture. In fact, no changes with respect to prior work, with respect to the AMBIT work. This framework is SIMDRAM, an end-to-end processing using DRAM framework that provides a programming interface, an ISA, and hardware support for efficiently computing complex operations, providing the ability to implement arbitrary operations as required, and using making use of DRAM as if it was a massively parallel SIMD substrate. The SIMDRAM substrate basically is the same as the AMBIT subarray that I showed before the break, but it makes use of 2 additional techniques. The first one is the vertical data layout, meaning instead of placing data horizontally, as the entire words horizontally with bits in different bit lines of the same row, as we normally do in DRAM, we need to use a vertical data layout, because that's the only way that we can shift bits, that we can move carry out bit of bit 0 to the addition of bit 1. So that's the first thing that we need to do. This vertical data layout, which has some drawbacks, as we will see, but also some pros or some benefits with respect to the horizontal layout. And the other thing is that instead of formulating the complex operations in terms of and, or, and not, which is what we normally learn to do in the school, here we take advantage of majority-based computation, because we all know that and, or, and not together are a functionally complete set, which means that we can implement any operation using them. But it turns out that majority and not are also functionally complete by themselves. And because AMBIT, or the proposals that we have just discussed before the break, in reality, what support are majority operations, activating 3 rows at the same time, and the result will be the majority of the bits that are in those 3 rows. We take advantage of that majority operation and not using the inverter implemented with the dual contact cell that I described earlier. And this way we can achieve higher performance and higher throughput than what the original AMBIT proposal provided. So this is the SIMDRAM framework. The SIMDRAM framework has 3 different steps. We are going to describe them quickly from a user input that is the desired operation, typically represented with and or not logic. The first thing to do is to obtain the majority not logic representation, and then turn that in step 2 into a sequence, an optimal sequence of DRAM commands, basically activate and pre-charge operations that are the commands that we need for row clone or for AMBIT operations. And by using those, we create sort of a microprogram that is the sequence of commands that the memory controller is going to execute when we want to execute a new operation in DRAM. We will have obviously an enhanced memory controller that is able to read this microprogram and execute it properly with a control unit and send the commands as needed to the DRAM chips. So let's start describing the step 1, how to generate the majority not logic from the and or not representation. This is the basic idea. We have this circuit here that might represent whatever. It's an addition, if I believe. Actually, this is a calculation of the carry out, as you can see. So the first thing that we can do is converting these into a naive majority-based representation, where we are just replacing each and or with a majority gate that takes one of the inputs equal to 0 or 1, depending on whether the original circuit has an and or an or. Yes, an and or an or. And this gives us a majority not implementation that is unoptimized, but we can further optimize using a greedy optimization algorithm that was proposed by prior work that you can read at the bottom. And using this algorithm, we can obtain a more compact majority not based representation of each individual operation. And because it's more compact, it has less majority gates. So that means that it will be more efficient. It will be faster on the SIMDRAM framework. So now that after step 1, we have the majority not logic, we can generate the sequence of DRAM commands to execute those majority and not operations inside the DRAM subarray. And in order to generate this microprogram, which is basically a series of microarchitectural operations, a series of DRAM commands, we generate this microprogram. And in order to generate this microprogram, we need to complete 2 tasks. The first task is to allocate DRAM rows to the operands. So the first task is to say, okay, where am I going to place the operands of the operation that I want to execute inside DRAM in each of the subarray bit lines? What are the rows that we are going to use? And second, what's going to be the microprogram itself. So what's going to be the sequence of DRAM commands to execute those operations. Remember that this is a subarray organization. At the bottom, you can see the designated rows, the compute rows, those that we can activate. I mean, they're connected to the row decoder that can activate 3 rows at the same time. And on top of them, we have a row full of zeros, a row full of 1 for initialization, or if we need to do and or, and the rest of rows are the regular rows that simply store data. So there are several constraints when coming up with an allocation algorithm. There are a couple of constraints indeed. The first one is that there is a limited number of rows that are reserved for computation. That's something that we have to take into account, and that's important and necessary because remember, we didn't want to have very complex modifications to the DRAM subarray. So that's why only this a small row decoder. And the second constraint is that the ambit operation or this activate pre-charge operation, this triple row activation has a destructive behavior. What that means is that when we activate 3 rows at the same time, regardless of what's the values that these rows contain in the beginning, let's say 1, 1, 0, if the result is 1 at the end of the operation, the 3 rows will contain the same, or the 3 cells in the same bit line will contain exactly the same value, is 1 in the example that I gave. So that's something that we have to take into account, even though at the same time, we can also take advantage of that. Because if you have the result in 3 rows, that means that you have 3 copies of the result, and you can use them for later steps of your algorithm. So in task 1, the allocation algorithm that is basically saying, okay, where am I going to place these 3 import operands, A, B, and C in? Because we only have 3 of them, we can place them directly in the free compute rows. So the algorithm, the first thing that the algorithm does is allocating data in the compute rows themselves, because this way we won't need to copy from one data row to one compute row. We are saving row copy operations here. And then we can do the triple row activation, and then we obtain the C out value, which is the result of this specific function. The second task is to generate the microprogram, and we are going to generate the microprogram after having allocated the operands. And the microprogram simply says, where do I have to, so what's the sequence of commands that I need? So for example, assuming that A, B, and C in are not in the compute rows from the beginning, they are in normal rows. We first need to row clone them, to copy them to a reserve row, to a compute row, A, B, and C in, and then we need to execute the majority. That is a triple row activation and pre-charge operation, right? And finally, copy the result to the destination row. So this is the initial microprogram. The SIMDRAM framework in this step 2 also applies some optimizations that are possible to do, like for example, coalescing row copies. Basically, if you have to copy one row to 2 different compute rows, you can do that at once by activating the 2 destination rows at the same time. So that's coalescing a row copy. And also, we can sometimes merge majority and row copy operations, because in the end, in a majority operation, you are doing activate, pre-charge. So the second activate can activate the destination row in the subarray, wherever it is. So that's basically the thing. There is an initial microprogram and then some optimization steps that can be applied in order to optimize the microprogram and later make it faster. So once we have the microprogram, we can go to, well, we need to store it in DRAM for future use, and we also create or have created a new SIMDRAM instruction. SIMDRAM instructions are called BBOps, and this SIMDRAM instruction could be added to the ISA, to the CPU ISA, and using the CPU program. using the CPU program, as you can see here on the left-hand side, and whenever the pipeline finds, the CPU pipeline finds this sort of instruction, sends it to the memory controller, and the memory controller will be able to decode it. How? By going to DRAM, loading the microprogram into the SRAM memory that the memory controller has, and at that point start issuing activate and pre-charge commands to the DRAM chips. So that's a basic operation. Here it describes a little bit how the SIMDRAM control unit does with the microprogram. So that's the basic idea in the 3 steps of the SIMDRAM framework. You can take a look at our paper or other considerations related to end-to-end system integration. One of the things that I wanted to mention here in this presentation is how to transpose data, right? Because remember, in DRAM conventionally and the way that the CPU understands data is in a horizontal layout. Consecutive words belong to the same cache line and they are accessed at the same time. But when it comes to using memory in the SIMDRAM mode, let's say, we need to have data placed in a vertical manner, right? So we need a way of doing this transposition. This is basically a bit transposition. It's something that we could do in software for sure. And it would have some overhead, but in some sense, it would be similar to the transposition that I mentioned that the current Upman system does in the runtime library. But in this paper, we propose a transposition unit that it's placed in between the last level cache and the memory controller, and as you see, and it has some buffer in the buffer, in this transpose buffer. We start keeping several cache lines until we have the number of cache lines that we need to do the bit transposition. That's how it, I mean, it's a relatively simple design, as you can see, but it does the job. There could be also other ways of doing this bit transposition. You could come up with a subarray design that allows you to read data in a vertical manner or in a horizontal manner. And in fact, if I recall correctly, there have been some past proposals doing that. I remember one paper from Micron in 2015 that allowed a way of accessing data vertically or horizontally. We didn't want to go for that approach in this paper because we wanted to keep the modifications in the memory subarray as minimal as possible. So this transposition has low impact on the throughput of SIMDRAM operations and also very low area cost, as you can see. And now we go to the programming interface. There are new instructions that can be used or should be used in the CPU program. Among these instructions, we have the initialization that is basically indicating to the transposition unit what are arrays, what are addresses, and what's the size of those arrays that need to be transposed when copying to the memory or when reading from the CPU or reading by the CPU from the memory. There are also these BBOPs that I mentioned earlier. We'll have one new BBOP for every new operation that we design and implement. They might have a single input operand or may have two input operands. That's the two types that we consider in this work. And then there are also predication instructions because SIMDRAM also supports predication. It's not the most efficient thing, but it's basically the way that we can implement control flow execution. So just let me give you an example on how to write code using SIMDRAM instructions. Here on the left-hand side, you can see some C code. Basically, is going over several arrays, A, B, and C, and performing some operation based on some condition, right? So if A of I is greater than the predicate, then do the if not, do the else. So it's an addition or a subtraction, as you can see. How is this code translated into SIMDRAM code? We need to first indicate that arrays A, B, and C are going to be operated on by SIMDRAM, so they will need to be transposed when copied to the memory subarrays. Then we need to have an BBOP_add that is going to perform the addition. We also need to have a BBOP_sub to perform the subtraction. And then we check what's the, for each of the values, we are going to generate one mask that represents the predicate. So depending on the values, the predicate bit that we are going to have in this mask, in each of the bit lines, we will do if or else. So that's basically what the SIMDRAM code looks like. So as you see, the drawback of this is one typical drawback of predication, that we have to do the add first, then the subtraction, and then decide what we write into the destination using the predicate that we obtain with this BBOP grader. But at least we can do it. We support it. And whenever you don't have potential divergence, it's going to be much more efficient. So you can find many more details in the paper about the integration and about how to write code, etc. And now if you want to very quickly take a look at some experimental results, we compared these to multi-core CPU, a GPU, a Titan V, and also to the state-of-the-art that was Ambit. The key difference between these realization of Ambit and SIMDRAM is that in SIMDRAM, we are using majority-based computation, while in Ambit is and or not based computation. So in that sense, there is where we are going to see the performance difference. Using majority directly is way more efficient on this architecture. We evaluated 16 complex operations. You can find them there, absolute value, addition, subtraction, bit count, equality, greater, equal, predication, ReLU, etc. And also 7 real-world applications that make use of these complex operations. For throughput analysis, for the 16 SIMDRAM operations that we implemented, we can see very good speed-ups with respect to CPU, GPU, and Ambit. Only with respect to GPU, we are not able to outperform the GPU when using just a single bank in SIMDRAM, but notice that this is DRAM, right? So we can exploit bank level parallelism, and as soon as we start using 4 banks or 16 banks, we can clearly outperform the Titan V GPU. For the energy analysis, we can also see quite interesting energy savings. DRAM is more energy efficient than the other devices, and for the comparison to real world, for real world applications, we see also similar trends. So yeah, you can find many more details in the paper, evaluation about reliability, the overhead of data movement, the overhead of the transposition, area overhead, etc. So this is the SIMDRAM work. If you don't have any questions, I will go with the second part of this presentation, and then we will go with Manuel for the next invited talk. Now the question is processing using memory in DRAM really feasible? Is this, I mean, all these proposals that we have just discussed in DRAM, Ambit, Roclone, is that something that can really be done in real DRAM chips? We believe it is. We believe it's feasible, and this is something that indeed was shown in Micro 2019 by these folks from Princeton in this compute DRAM work. They showed that it's possible to do row copy operations and even Ambit operations, even bitwise operations in some chips by violating DRAM timing parameters. The basic idea is to issue, activate, and pre-charge commands at a reduced latency. So that's why they are violating the normal DRAM parameters. And by doing so, they are able to open rows these rows are going to start sharing, or the cells in these rows are going to start sharing their charge with the bit line. But because the activation and pre-charge operation happens so quickly, it's not possible. I mean, the sense amplifier doesn't even get activated. So it's not able to amplify the charge deviation in the bit line. So for example, for the row copy operation in compute DRAM, how do they do that? Observe that here we have two rows, R1 and R2, and here at the bottom, we have the sense amplifier. So the first thing that they do is activating row 1. No, so as soon as you activate row 1, the cells there start leaking charge onto the bit line. So in this case, this cell here is charged. So the voltage of the bit line starts increasing, but then they need to issue a pre-charge command, right? The point is to issue this pre-charge command very quickly so that the sense amplifier doesn't really get active. And when you go and activate the second row, in this case, row 2, because the bit line is already over BDD over 2, the charge in the bit line starts going and filling the cell in the destination row. So that's the basic idea. First, one activate very quickly, one pre-charge, and finally, second activate when the bit line is above half BDD. And by doing so, you're basically copying the contents of row 1 into row 2. For the bitwise operations, in this case, bitwise AND is what we can see in this figure here. It's slightly more complex, and it doesn't work for all the chips that they tested, as you will see later. But the point is that depending on, I mean, the basic idea here is that the row decoder is designed in a way that when you go from activating one row to activating another row, the index values in the row decoder change bit by bit, let's say. So we have first of all activate row 1. Finally, we will activate, so first of all, we will activate row 1, then we will activate row 2, but because row 1 has address 10, and row 2 has address, 01, and row 2 has address 10, the row decoder first changes one bit, this less significant bit, and then it changes the second bit. So what happens, because the activate, pre-charge, activate sequence is issued very quickly, what will happen is that in between, the second row, in this case, row 3, will be open as well, just for a few microseconds. So that's the point here. So observe how we first open row 1, the row starts sharing its charge with the bit line, because the bit line in this case was at half VDD, and this cell is discharged. It starts charging. At this point, we pre-charge and then activate row 2. But while activating row 2, we first open row 3. So row 3 starts sharing its charge with the bit line as well, rising in this case the level of the voltage in the bit line, again back to closer to half VDD. So and finally they end up opening R2. So when opening R2, R2 starts leaking charge as well. So the three of them, as you can see in this part of the figure, are sharing their charge with the bit line. So that's why in the end the AND operation happens, or the majority operation happens. It's an AND simply because one of the rows has a constant value equals 0. So that's why they talk about AND in this work. And here you can see, yeah, T1, very short T1, which is the time between the first activate and the pre-charge operations, so that the sense amplifiers are not activated. And then T2 is also very short. This is the way of opening R3 first and R2 next, and finally obtaining the majority result in the bit line and in the 3 cells after the next pre-charge operation. So for the experimental methodology, they tested this on real chips using the SoftMC, that is a FPGA-based memory controller that was developed in the Safari research group. They tested many different DRAM modules, 32 different modules with around 256 DRAM chips, and they did this proof of concept, basically what I explained in the earlier slides, sending activate, pre-charge, and activate commands to the DRAM. They were playing with different values for these T1 and T2, as you can see in this slide, right? For different combinations of T1 here on the y-axis, let's say, and T2 in the x-axis. And for those, they got different success rates, right? As you can see, the bluish combinations represent row clone operations or row copy operations. And then the green ones represent and OR operations or AMBIT operations. As you see, they are not so much frequent, but at least some of the chips were able to do them. So this is the Compute DRAM paper, as I said, presented in 2019, and by taking the ideas or some of the ideas in this paper, we proposed an end-to-end FPGA-based framework for processing in DRAM, and that is called PyDRAM. The goal here is to develop a flexible platform to explore end-to-end implementations of processing using memory techniques. It has software components and hardware components, as you'll see, and it's basically an FPGA where we implement a RISC-V system and memory controller, a custom memory controller that is going to be able to execute processing using memory operations onto the DRAM that is exactly here. This is the entire PyDRAM workflow. We can have a user application that makes use of the library called PUMOLIP that provides these row clone operations or other processing using DRAM operations that you want to implement. In particular, in this work and in the paper, you can see row clone operations and also operations for random number generation. So the user application can directly use this PUMOLIP. These instructions are going to be decoded by the chip, by the processor, RISC-V processor, the Rocket chip, and then using store instructions, they are moved, they are copied to this PUM operation controller that is basically the controller that is in charge of issuing the required DRAM commands onto the DRAM module. So that's the PyDRAM workflow, and the entire PyDRAM workflow. I mean, all the details, you can find them in the paper. This is, I think, a very interesting experimental platform for these kind of operations and that are really necessary, because it's not only like having the theoretical idea of activating multiple rows at the same time, or using a simulator, or even using an FPGA controller as Compute DRAM Fox did. I think it's also very interesting and necessary to face the challenges that the integration in real systems may have, and that's basically what we try to do with this PyDRAM framework. The work is accessible. I mean, you can find the paper in arXiv, and also the repository is publicly available. And here you can see just that for illustration, some performance of row copy and row initialization, and the throughput improvement, like about 2 orders of magnitude faster than doing these operations using the CPU. As I said, PyDRAM is open source, so you can download and play with it. And if you want to learn more about it, and even with a tutorial on how to use it, I can recommend you to take a look at this talk that Ataberg, who is one PhD student in the Safari Research Group, delivered a few months ago. So this is all for this lecture. for now. So now I am going to hand over to Manuel, who is going to give the next invited lecture. Thank you very much for your attention. I don't know, guys, if you have any questions. If you have, please go ahead.
When you do operation, the majority of the road control, right? The road flow and road traffic with any road, right?
Mm-hmm.
So is there an impact from how long ago the road was refreshed? Because the cells leak over time, right?
Yes.
So does the copy get less reliable if it's been refreshed a long time ago or something like that?
Yeah, well, that's a really good question. Actually, I think that's something that, I mean, in the end, DRAM or DRAM rows are refreshed every certain time, because that's the time that you can tolerate that leaking, right? So what we do here, when we want to copy one row, regardless of when it has been refreshed, what we do is opening this row. And if you open this row and it can be read, because it still has the charge that it needs to have, that it should have, it should be fine for the row copy as well, because as soon as you open it and then you activate the sense amplifier, the sense amplifier is going to amplify this deviation and put the bit line voltage at the appropriate level. So yeah. Mm-hmm. Okay, thank you for the question.